Modern physics and discrete mathematics face a structural crisis at their foundations. We consistently build our models on assumptions that are rarely subjected to rigorous structural auditing, specifically how we handle the boundaries of space itself. This begins with the philosophical assumption of ex nihilo construction, the idea of creating structure out of nothing. Classical relativistic models posit initial structures, like the empty set or completely frictionless vacuums, as axiomatic truths without explaining their origins or geometric limits. When we try to bridge discrete mathematical logic with these continuous manifolds, unresolvable error gaps naturally emerge. Standard calculus and continuous to discrete mappings traditionally dismiss these gaps as numerical artifacts, floating point exhaustion, or simply failures in our approximation models. The theory of infinity, or TOI framework, proposes a rigid counterthesis. By applying strict ontological parsimony, the principle that models should not multiply entities beyond necessity, this canon dictates that these mathematical gaps are not arithmetic optical illusions. When a discrete mathematical lattice attempts to map onto a continuous curved surface, it cannot perfectly conform. The grid aggressively vibrates as the points fail to align. The system is experiencing mathematical resistance. We locate the physical analog to this mathematical resistance in the 1950s work of mathematician John Nash. Nash proposed an alternative quadratic theory of gravity to explain cosmological redshift, the lengthening of light waves from distant galaxies. Instead of attributing this solely to the expansion of the universe, Nash hypothesized that light experiences a literal friction as it propagates through a fluctuating, corrugated gravitational field. Our objective is to test this principle mathematically. We will execute a sequence dilation, intentionally wrinkling a discrete mathematical sequence to calculate the resulting topological friction and measure its exact energetic cost. Reclassifying a mathematical error as a conserved physical property forces us to discard the assumption of a frictionless void. Doing so completely overwrites how we understand the generation of mass and the structural boundaries of the universe. To measure this friction, we must first map an unperturbed baseline. We use the Tribonacci sextic lift, a continuous polynomial morphology used to govern three-dimensional spatial transitions within the TOI engine. The foundation of this baseline is the standard Tribonacci sequence. This is a mathematical progression where each term is the recursive addition of the previous three integers. We elevate this one-dimensional integer sequence into two foundational continuous states. The first is the winding genesis, or apophatic state, which uses an alternating sign parity. The second is the manifest state, which operates with uniform addition. In the apophatic column, alternating signs force a real root horizon of 0.737, with an operator extraction limit of 1.839, trapping complex roots. In the manifest column, the real root horizon decays to 0.544, but the complex roots remain locked to that exact 1.839 limit. Placing these two sextic limits side by side reveals the law of topological mass exchange. This law states that the total mass of the system is perfectly conserved, merely swapping dimensions based on the parity of the sequence operators. The heavy real mass of the apophatic state swaps flawlessly with the heavy complex mass of the manifest state. Topological tension migrates directly across the real imaginary boundary without any loss. As long as the sequence parity remains unbroken and contiguous, these dimensional transitions remain perfectly symmetric. The system operates entirely without friction. We can intentionally break this symmetry by introducing a primary disruption operator known as the skip-1 dilation. Instead of toggling sign parity, the skip-1 dilation alters the index spacing itself. It functions by aggressively skipping every other integer rung of the Tribonacci sequence. Removing that contiguous additive chain physically stretches the polynomial geometry. The space between the remaining numbers becomes a wrinkled, corrugated gap. To determine the infinite geometric rail of this severely gapped sequence, we deploy the J13 knot infinity mapping operator. This acts as a boundary function to collapse the polynomial into a cubic morphology. We extract the underlying symmetry through a mathematical normalization process. By substituting our dilation mapping and factoring out the common scalar denominator, the dilated cubic equation collapses. This reveals a pristine mathematical seal. Beneath the violent stretching, the real dimension locks to an exact invariant limit rail of u cubed minus u squared minus u minus 1 equals 0. When we test this empirically at finite steps like rung 7, the computation seamlessly tracks this infinite limit, arriving at a real root horizon of exactly 0.401. The finite mathematical computation flawlessly chases the algebraic limit. Because the real root geometry completely accommodates the spatial stretch without loss, the structural cost of this dilation must be isolated entirely within the complex plane. The true ontological anomaly lies buried in the complex plane. This is where the mathematical rules begin to break under the tension. Recall John Nash's hypothesis regarding non-uniform gravitational fields and cosmological redshift. In his framework, a photon loses energy and lengthens its wave, simply because it must navigate the fluctuating, wrinkled topography of deep space. This physical concept maps directly to pure mathematics through the Nash-Moser theorem. Specifically, it mirrors a geometric barrier known in functional analysis as the loss of derivatives. The complex roots of our skip-1 sequence act exactly like Nash's photons. As these roots attempt to forcefully map a corrugated, rigid sequence onto a smooth, continuous manifold, the iterative algorithm shreds the smoothness of the function. They experience severe topological friction. Because the function is actively losing derivatives, we cannot simply look at the final magnitude of the root. We have to execute a geometric phase extraction mid-transit to measure this severe resistance before the calculation halts. To filter the chaotic data generated by this metric fluctuation, we introduce a mathematical tool known as a phase angle smoothing operator. The formulation is the square root of the absolute ratio of the imaginary to the real component. Taking this root mathematically dampens extreme fluctuations, forcing the gapped sequence into a stabilized trajectory, converging on a precise limit of 1.0506. This mathematical filter functions precisely like Jürgen Moser's topological operators. It artificially truncates the high-frequency spatial wrinkles and forcefully projects the data back into a measurable continuous space. By tracing the roots of the parent cubic equation, we confirm that this finite empirical extraction is permanently locked to an exact infinite limit. The successful deployment of this smoothing operator proves that the complex root's failure to smoothly embed is not an arithmetic hallucination. It is a quantifiable geometric barrier that we can mathematically isolate mid-transit. To understand the energetic cost of this barrier, we measure it against the ultimate baseline of the TOI canon, the golden vacuum. The golden vacuum is a perfectly flat zero-point manifold. It serves as the minimal, unperturbed geometry upon which all spatial boundaries are drawn. Comparing the smoothed phase limit directly against the continuous golden vacuum, the sequence explicitly misses. It approaches the baseline, but permanently fails to intersect. The discrete phase is blocked, leaving an unsealable gap between the rails of roughly 0.00085. Under classical mathematical programs, this microscopic failure to close would be discarded to preserve the assumption of a frictionless universe. But the strict editorial law governing this system relies entirely on distinguishing friction from fiction. Because this delta gap is mathematically locked by an exact limit, it cannot be discarded as an untyped error. It is permanently typed as Nash-Moser Topological Friction. To process this mathematical heat, the system uses a specialized cybernetic loop known as the Amanda root engine. This engine is a continuous state-space matrix designed to metabolize continuous dynamics into actionable discrete updates. The Amanda engine executes a fate check, an intentional audit of the system's harmonics. When it isolates this permanent gap, the engine metabolizes the residual friction through a boundary hinge. It aggressively feeds the mathematical tension forward to successfully update the discrete state space, preventing the entire algorithm from crashing. The permanent presence of this topological drag proves that geometric boundaries cannot be drawn ex nihilo. The fundamental architecture of reality is not built upon frictionless voids, but rather it is dynamically generated by the exact permanent friction experienced precisely at the boundary where the discrete finally meets the continuous.